Hi everyone, and welcome to the second lecture with Professor Reid. Please go ahead.
Yes, so today the main group of interest is SO10 and its spin double cover. So normally spin double covers are constructed using Clifford algebras. Here I want to do it by hand without using anything. So I'm starting off with combinatorics in a lattice. Yes, so take the lattice Z6 with this Lorentz dot product. So, mathematicians and physicists probably usually have opposite notation. It would be perfectly reasonable to take minus this dot product. In other words, time is negative and space is positive. Anyway, it doesn't make any difference. Yeah. So in this lattice, I ask for all the lattice vectors that satisfy v squared equals -1. So for example, 0, 1, 0, 0 is obviously like that. And k times v equals 1. Yeah, and I don't know how to get rid of the. You can easily do this. I mean, define a function which is a dot product, say what the characteristic vector is, and then just ask for the set of all 6 tuples with the property that dot product of it v with v is -1 and with k equals 1. So you get what I said. I mean, of course, you can do this by hand in a minute or two. Yeah. So we're not very far away from the combinatorics of the root system D5. Yeah. So if you're doing algebraic geometry, then you have something which is called dp4, Delpitzer surface of degree 4, which is what you get if you blow up P2 in 5 points. So this is practice for next week when I want to blow up P2 in 6 points. In any case, the vectors I wrote before are lines on this surface. They're cohomology classes of lines on this surface. Yeah, and 19th century people loved incidence geometry, and so if you write an abstract graph with 16 vertices corresponding to the line, and you join them by an edge, if the lines meet, yes, the class of line 1 and class of line 2 have cut product equal 1. Yeah, then when you do that, I'm telling you the result, it's not hard. They form the vertices of a graph. The graph is a 5 cube modulo antipodes. Yes, and it's a 5 cube. So if you've got one vertex of it, it meets 5 neighbors. So one of these, if I go back to the first page, that's this last one, is different from, is different from the others. It's in some ways the simplest. It meets the 5 guys called Li. Whereas Li meets Mij and Mj and doesn't meet the other line. Yes? So, you know, this is 19th century incidence geometry. Right, so this is how to find the symmetry group. So, you know, if it was a symmetry group in the cube, you'd just say, obviously, 5 factorial, because you can, you know, permute the 5 coordinates anyhow you like, and you can take each xi to minus xi. So here I'm doing something slightly different because I want to do the symmetries of the 5 cube modulo antipodal involution. Yes? So here is one particular, slightly idiosyncratic order 2 in, symmetry of the graph. Yes, you'll see why I want it later. So you ask each of these symmetries what they do with the 16 lines I gave you. And this one, R0, does this. Yeah. So, you know, you have to check that it's compatible with antipodal involution. Yes. So now I'm going to do 5 reflections. Yes. So if I swap 1 and 2, then of those 16 lines, everything that has a 1 in it goes to the same thing with the 3. 1 goes to 4, 1 4 goes to 2 4, and so on. And I numbered the lines 1 to 16, and that turns out to be that. Yes? So these are 5 symmetries of a set of 16 elements, and the 5 reflections satisfy the Coxeter relation for the Deakin diagram D5 and generate. I don't know if I have the Deakin diagram. So the Deakin diagram is of D5 is this. It's 5 vertices. Yes, and this specifies a Coxeter group. So that means each of these guys have correspond to a reflection, and the reflections commute if the 2 guys are not joined, and they have angle of 120 degrees if they're joined by a single link. Yes. So D5, and its order is what did I say? 1920, which is 2 to the 4th times factorial 5. Yes. So next week I'll be adding 1 vertex here to get E6. And the value, that's the Coxeter group, or the violet group of the root system D5. Next week I'll be talking about the value of E6, which is, how do I remember it, 551,840. So, you know, there's a little configuration there, and 19th century people would write down things associated with them and calculate them. When you get to about 51,840, you don't really think of this as a group that you can work with in a very straightforward way. Okay, so I said this is D5. The root lattice is obtained by, so I'm in this Lorentz lattice with 1 plus and 5 minuses. Yes, and it's unimodular dot product. Right, when I take the orthogonal complement there, this K was positive. So this, when I take the orthogonal complement, I get even because K is a characteristic vector and it's negative definite. It's a lattice of rank 5 and discriminant 4. So, any other mathematician than an algebraic geometer would choose minus for the dot product. In any case, you can, what's a plus or minus sign between friends? Yes. So above, I told you how to find the 16 lines. Now I'm going to change the problem and ask vectors in this negative definite K orthogonal satisfy V squared is minus 2 and orthogonal to V. So when you do that, you get 40 roots. Yes, so E1 is a root. You can check that it's V squared is minus 2, that squared is minus 1, that squared is minus 1. And it's orthogonal to V because that's plus 1, this is minus 1. Yes, and E2 likewise. So if you calculate the intersection pairing of E1 and E2, you get plus 1 from this. Yes, and that means that if I can draw a graph and I get the Dinkin diagram, E1 joins to E2, E2 joins to E3, E3 joins to E4, and this E0 joins to E3. Right? So saying their roots means that in the Euclidean lattice they live in, with that negative definite in a product, I can do reflections in a root, and the reflection in any of the roots gives you, takes the 40 roots to the other 40 roots. So that group I told you, of 1,920, has, a few hundred of the, it has 40 roots and 40 involutions in those roots, 40 reflections in those roots. And it has plenty of other, plenty of other continuity classes of order 2. Yes. Now, these are the positive roots. So in a root system, it's a theorem that any root, any vector satisfying these conditions, is either a positive integral combination of the simple roots or a negative integral combination. So if I do E1 plus E2, I get one of these guys. Yes? If I do E1 plus E4, E1 plus E3, I start getting these guys. Yes? Anything with E0 in it must have a 1 in the front. Yeah? So we're in the orthogonal complement of K, but we definitely use this first vector. Yes. So the reflections in the simple roots here. So these are reflections of this 5-dimensional lattice, but they also act on the ambient Lorentz space, and so they commute those vectors around. Yes? So I want to get to this variety, which I call orthogonal Rachmanian 510, or spinor variety. Yes? So I want to write down polynomials in a projective space. Yes, and coordinates in my projective space are going to be these things, V1, V2, V3, V4. I mean, they're the lines from the first page. 16 lines form coordinates in a 15-dimensional space containing this principal, this smallest homogeneous space. Yes. So let's take 4 lines like this, 4 lines in space, with the property that they meet as a ring. Yeah, I've got 4 lines, the straight lines in P4. I'm sorry, there are 4 lines in P4, and they meet as a kind of cycle, as a wheel. Yeah, and that means that on DP4 they form a curve of genus 1, and they move. That forms a hyperplane section of DP4. So if you take a general hyperplane section of DP4, you get an elliptic curve, and these, if I take V1 plus V2 plus V3 plus V4, which is like that, I get an elliptic curve that has had 4 little accidents. It's broken up as a union of 4 straight lines. Yes, so it turns out there are 40 squares of lines, and they move in linear systems which have 4 of these, 10 different linear systems. Yeah. So I told you about the 5 cube. The 5 cube, one vertex, each vertex is joined by a line to 5 neighbors. And if I've got 2 neighbors, I start from one vertex and I go along axis 1, and then I go along axis 2. Then those span a square face. Right, so this has got this 5 cube has got 5 choose 2, which is 10 square faces coming out of each vertex, and then 10 second neighbors. Okay, neighbors, I mean the vertex opposite the origin in a square. Right. So I've got 2 to the 5th over 2 pairs of antipodal vertices. I'm sorry. So here, L1 and M12, I mean, you could just look this up on the screen from the first page. L1 and M12 meet, both of them meet, I'm sorry, L1, M34, L1, for God's sake, L1 meets L34, L34 meets M15, M15 meets M12, and M12 meets L. So these are squares. Yes? So this is a pencil of elliptic curve hyperplanes of the surface, and they, if I force them to contain L1 and L2, then residually, usually I get a non-singular phonic, but 4 particular fibers have the phonic breaking up. Right, now, using these 16 lines, I introduce 16 variables, so I can call them x1 to x5 and then y2 to y45 z, following the terminology, or sometimes I might just want to think of them as 16 elements. Yes? And I have these privileged 40 squares. Yes? So I write down this polynomial, right, which is just the sum of the 4 quartic monomials, I'm sorry, the sum of the 40 quadratic monomials I come by running around one of the squares. Yeah? And this one has plus or minus terms. And I can explain that. I'll explain next week a little bit how that works. This is called the Coxeter-Brewer shortest length algorithm. So I have a reflection group with named generators. So every word in the group is, every element of the group is a word in these generators. And each of these can be written as a shortest length word. So if you're running around, for example, if you know what it is, you might run around the Cayley graph of the group to get from one element to another. And then there's a shortest element. So, this is either plus 1 or minus 1. It's minus 1 if you get from the first square to the second square in an odd number of moves. Yes? So, in this polynomial, the 16 variables and the quartic monomials and the signs on the quartic monomial are all given, all specified by the Dinghin diagram D5, and then by the root system. Yes? So now I'm going to take that polynomial phi. So there's this huge polynomial with 40 quartic terms, and take partial derivatives with respect to pairs of intersecting lines. Yeah, so you get each of these, I think, about 4 times, but these are 10 quadratic polynomials. Right, so if you look, one of these has zx1 in it. Yes, where does zx1 appear here? It appears in the first monomial, it appears in the second monomial, and so on. So I say take partial derivatives, but there's no differentiation going on here. I'm looking at this polynomial, I'm asking, of all its terms, how many contain x1 and z? And then I'm just writing those down and dividing it through by the x1, z. Yes? So, I get these 10 beautiful equations. So we're going into projective geometry here. I have space with 16 coordinates. I have 10 equations. Yes? So I define a variety using it. The variety is a cone at the origin. Every one of these equations defines a cone at the origin, a cone of rank 8 in 16 variables with the vertex at the origin. Yes? And then if I take spec of the ring x1 up to x16 divided by these 10 equations, I get the affine cone over the Grassmannian. Or if I take not the spec, but the proj, I get the projective variety. Yes? So now I'm going to divide this. I'm going to divide this affine cone over a Grassmannian. So I'm writing affine Grassmannian. This notation comes from my paper with Crosty, which explains what these are in much more detail. Yes? So I can ask for an algebraic torus that multiplies them. So at the end, I'm going to get this thing here. Can you see when I move the pointer? Yes? So how do I get that? First of all, I take the biggest torus you can imagine. I'm just thinking of this 16-dimensional affine space in a trivial way as a toric variety. So it has a big algebraic torus that multiplies the 16 variables by independent scalars, independent non-zero scalars. By the way, I should have told you, I'm writing this GM for the multiplicative group. So that's a little note I should have said. I'm writing GM for what most of you probably would prefer to call C star, yeah, the multiplicative group. So the reason for writing GM is because GM multiplicative group is a group scheme defined over the integers, whereas C star multiplicative is the C valued points of this. So somewhere at the back of this, I have in mind that I'm doing scheme theory, although I'm really doing projective variety. Yes? So now, I have these 10 spinor equations, and I've got this enormous algebraic torus that acts on it, and most of that torus does not leave these equations invariant. So I want the equations to define an invariant subvariety, and in order for that to happen, I don't need the equations to be invariant. It's enough to know that they are character functions or eigenfunctions of a torus. Yes? So there's what we're doing is we're taking, if I was asking for this 6-dimensional neuroseverity group, or second cohomology group of the Del Pezzo surface, I'd be doing exactly the same calculation. I'm taking the 6 lines and I'm saying all squares are equal. So remember that polynomial is made up of squares. It's the original big phi was made up of squares, and asking for this phi to act on my 10 spinor equations by eigenfunctions is the same as asking it to act on phi by, sorry, this is not grammatical. Yes? So the del Pezzo surface has a second Betti number 6, or Lewis-Array group of rank 6. Therefore, there are six of these 16-dimensional toruses. The torus of rank 6 in there leaves the affine Grassmannian variety invariant. It multiplies each of its equations by the same scalar. Right, now, my aim here is, I've got O Grassmannian in P15 mistyped, yes? I want to say that I expect this variety to have a lot of symmetry, and that should be spin 10. Yes? Now, I made a start on that because this big torus I've got, GM6, is leaving fixed the variety. It's leaving fixed this thing. So I'm going to declare at some time that, this is acting on the affine code. It, of course, contains the trivial C-star action, the ordinary multiplication action that defines projective space. So the thing that is acting on the projective space is the torus that G5, G6 divided by the diagonal torus, G5. So that is the maximal torus of the root D5. And I want to construct, so there isn't just, I have the maximal torus. So this is, I should have said, maximal torus of spin 10. Oh, SO10 is GM5. Yes, so that's rank 5, the D5. Yes, so this group here, this D5, the maximum torus, acts on projective space, and it takes the O Grassmannian to itself. Yes. So now I'm doing the spin. Now I'm doing the. I can also do its symmetry under this group of order 1920, right? So there's a lot of stuff actually on this variety. The problem with this is spin 10 together with this group of 190 is still only a 5-dimensional root. So, in Wednesday's lecture, I was talking about the matrix group, SL5, and then it had a diagonal subgroup. So if you only have the diagonal subgroup and permutation matrices, you only have a kind of thin slice of the group. Of course, it's very important in slice, but you don't have this missing all the roots of the root system. I want to have off-diagonal elements of the root. Yes? So in Lie algebras, Lie algebras are on the whole easier than groups because they are linear, because they are, so a Lie group has a Lie algebra, which is more or less the tangent space at the identity element. Yes? Now, in the theory of Lie algebras, you have a Sator subalgebra, which is an abelian Lie algebra of rank, in this case, 5. And then, so the 5, that's the H. So there's a 5-dimensional family of H. By the time you've chosen simple roots, you can write down something called, you can write down this combination of an element of the Sator subalgebra, so that's like an element of the diagonal matrix group, and then an element X, which is something like an upper triangular element of the group, and something Y, which is, so this X is a positive root, Y is the opposite negative root, right? And then they have this property. So this means this means they generate a subalgebra of the Lie algebra, which is SL2. And you can think of, if you want to, you can think of the Lie algebra as being entirely specified by, if it's rank R, rank 5 in my case, by 5 H's, 5 diagonal matrices, 5 upper triangular matrices, 5 lower triangular matrices, satisfying these relations. Right, and that's all the relations. This is called the Serre relations for a simple Lie algebra. Yeah. What I'm doing here is justifying this calculus giving me 6-dimensional space. So I said it is the same as the thing I'm writing down here is a 6-dimensional torus. It acts in a funny way on all of the variables. Right? I mean, it's all governed by the combinatorics of the root system that I described earlier. Yes? So, and then each of the quadrats, okay? So the calculation that leads to this is exactly the same as the calculation of the neural severity group of the Del Pezzo surface 4, dp4, obtained by, okay. Let me get on. Actually, this is the last slide. I can improvise a bit afterwards. Yes. So this is basically an erratum. When I started preparing this, I had the idea that we don't need to do anything. Already the value, the action of the maximum torus and the action of the value determines everything about algebraic groups. So that's true, but it doesn't apply immediately. And in this case, it's something that I was claiming to be able to do easily, and now realize that it's a little bit harder. Yeah. So I told you last time that when I was doing Restman 2, 5, it was 2 planes in 5 space. I've got a certain manifold or algebraic variety that parameterizes 2 planes in 5 space. Right, so here I'm I've got the root SO10, which comes by writing down, this is the standard quadratic form in 2 n dimensions, block matrix 0, 1, 1, 0. Right, it means we've broken up the space into 2 direct summands. One of them, each of them is isotropic, and the quadratic form here is evaluating one of these 2 spaces as the dual of the other. Right. So this is the Restman variety where the 5-dimensional isotropic subspaces. So everything I said last time about principal open sets and about tautological exact sequences and about the Chern characters and the spinner class of the tautological exact sequence, calculating the cohomology or the K-theory of the orthogonal Riemannian applies. Yes? So, you know, we've got a lot going for us. My spin variety is a beautiful variety. It's a parameter space, and I'm talking about the group which is its symmetry. Yes. So I told you I have this paper, joint with Crotty. It's, I think it's somewhere it's referred to on the poster for the lecture series. Yes. So here I'm writing down 2 particular ones of the 10 spinor equations, right? And then, you know, you just have to permute, bash them around by 1, 2, 3, 4, 5, right? So this is last time I said I'm going to take affine pieces. Yes. So I've got a projective variety. I set Z equals 1. Right now, you go to all of those previous equations, and I already pointed out that 10 of those equations have z in them. So when I set z equals 1, they're very nice, simple equations now. For example, if the z here, this is the x here in different notation in our previous paper. If I say x is 1, then I immediately get x1, x2, x3, x4, x5, and 5 other guys as linear, I'm sorry. I get the z appears in exactly 5 equations. And where it appears multiplying one of the lines that joins it. Yes? And if I eliminate the 5 variables, so I've got an equation saying 1 times the 5 variables, each of the 5 variables, equals something in the other variables. So in other words, I can just eliminate this and get in 15-dimensional projective space a 5-dimensional, 2-dimension 5, a 10-dimensional affine piece, right? And the affine piece is this IM. I is the identity matrix. So I'm saying where z equals 1, when I write 5 vectors that form a basis of z equals 1, the first 5 coordinates will already give a basis, right? And so I can change basis there so that this is the first 5 by 5 block is the identity. I'm just doing round column operations. And then the second element is a 5 by 5 matrix. I want this to be, I want the subspace of the row span of this 5 by 10 matrix to be isotropic, right? So I have to do this matrix times M, sorry, this matrix times the quadratic form times the transpose of the matrix. So when I do that, I get M is required to satisfy the equation that M plus M transpose equals 0. That means it's skew, right? So skew means that this is a 5 by 5 skew matrix. I wrote some of them last time, and I'm writing another one here. Yes? So there are 5, there are 10 equations, of which 5 are written in this special form. One of the variables, that's Z in my current talk, but it was X in my talk 15 years ago. I'm writing X times V equals the fraction of M. So, the other 5 variables, the 5 variables corresponding to lines meeting X, are not just determined, they're determined in this very symmetric way. Right. So I claim that with 1 or 2 hours of study, I'll be able to find elementary matrices here, matrices that are essentially diagonal plus 1 upper triangular block, and that these will play the same role as the H, X, Y in the cell relation for roots. Yes? So this is an erratum because I didn't realise until last night that I couldn't do this off the hand. So let me say. So I got my spinner variety over of 5, 10. Yes. So this is homogeneous symmetric space for SO10. Yes. So it has cohomology, even cohomology, that we know by a little calculation. Last time. Basically similar to as last time. Right. I'm going to tell you there's one thing that's different, and that is the following point, that if you want to embed over 510 in Pn, you need an ample alignment. Yes. So, let's do the very easy thing. Let's say that O orthogonal Riemannian 510 by definition is contained in Riemannian 510. Yes. So I told you about Riemannian 510, and you can embed that. This has a Fecha embedding in Pn, where n is. This is wedge 5 of 10-dimensional space. So that n is 10 choose 5 minus 1. Yes. Now, the problem with this is that this is an uncomfortably large number. Right. So let's ask again. This is a question. Is there what's the best ample alignment? And I told you that we know it's H2. So H upper 2 of O 0. So this is isomorphic to Z with a preferred generator. So I'm writing a line bundle, or L is O of 1. If I yes. And the problem is not invariant, not invariant under SO10. They're not defined. They're not defined. That I should have prepared this better to know what words to say at this point. Yes. So you know, if you've got a group acting on a projective variety, so if I've got V in Pn, right, I can, I have H naught of O of 1 coordinates, so homogeneous coordinates on Pn. And if I have, a group acting on V, the question about whether the action comes from a linear action on the coordinates is non-trivial. Right. So the thing that always happens is there always exists a central extension of G that does it, that acts on the coordinates, but not G itself. Yes, so this happens everywhere. I mean, this is the problem of linearization. Yeah, so what's happening here is that I've got a beautiful line bundle, what I've been talking about for the whole lecture, namely the thing that takes O, 5, 10 into P 15. Right, so with this number 16. Right, so 16 is quite a lot smaller than this number. Yes, so the thing that's happening here is that when I go to Rachmaninoff 510, you know, it has its own personality and so on. It has Fecha embedding. If I take the Fecha embedding and restrict it to this sub-variety, isotropic Rachmaninoff, the corresponding line bundle is divisible by 2. The O of, so O, let me write L subspace Fecha restricted to over 510 is twice L. L twice L spinner. Yes. So I mean, this is well-known group theory. There's a group spin 2n. That's a double cover of spin of SO 2n. Right. And this is traditionally constructed using Cliff analysis. Yeah. So, you know, if you're a physicist, then you've probably heard of Paul Dirac. I don't know if, you can probably see me. There's this gesture. I don't know if you can sort of practice this yourself. Imagine you got to hold a tray with a wine glass on it, and you're going to turn it like that. The tray with the wine glass is now in its original position. Yes. So I mean, you can also, if you look up Dirac belt trick on Google, you'll see people doing it much more heavily than I'm doing. Yes. That is a spin double cover. In the gesture I was doing, I was rotating in SO3, so 3 of course is not 2n, but the principle is the same. And above that, there's some other, not Euclidean space, some other space in which, you know, when you do, so Feynman, QED. Yeah. So let's pretend that space is 3-dimensional with one time direction. Yes. Then when you've got an electron moving through space, it has its moving position, and you might think the geometry of that motion is all controlled by Euclidean translations and Euclidean rotation, SO3. So Feynman's lectures or Feynman's book on QED says that's not the case. So the electron moving through space is carrying on its back a two-dimensional complex space, which is a representation not of SO3, but of the double covering loop. Yes. So, I mean, this is completely standard physics and completely standard mathematics as well. So, what I've got here is this embedding. I've got this really very, very simply defined algebraic variety. Just given by these 10 spinor equations, and the 10 spinor equations are entirely specified by the Latin diagram D5. Yes? And then if you work a little bit harder, which I haven't yet done, you will find a way of constructing the algebraic group spin 10, which is the double covering of SO10. Yes. So, I mean, I'll be doing the same thing for E6 in next Wednesday's lecture. Right. And then the mathematics gets harder. Yeah. So, Clifford algebras, sort of, everybody thinks that they're very simple things, but actually they're quite involved. So I said here that even an order difference over the reals, there's but periodicity, which you'll find in physics books on supersymmetry, and that is periodic with period 8. So, for me, this D5 corresponds to SO10, and the root lattice D5 has a description as orthogonal complement to a characteristic vector exactly related to K in Lorentz space. 1 minus 5. Right. D7, similar, that corresponds to SO14. And exactly the same. Well, it's not exactly the same. Yes. However, D4 and D6, the root that they have a root lattice where you need to add 2 dimensions to yet. So the thing I'm saying is, let me them as authorial complements in unimodular lattice. Right. So you know, let me just the technical mathematical thing I was saying is I've got a lattice cell. I can write L dual. Yes, this is hom in the million roots from L into Z. Yes, and then L dual over L. So, I mean, obviously, L is contained, L subset L dual, because I've got a quadratic form on it. Yes, and the index of L in L dual is the discriminant of the quadratic form. Right. L dual divided by L, this is the index subgroup. I mean, it's it's a finite abelian, it's an abelian group of of cardinality. This discriminant has order equal discriminant. But so D2n plus 1 has L dual over L equals Z mod 4. So that's what I used on my first page of my lecture. I said I can construct the root lattice of D5 by taking a unimodular 6-dimensional lattice and taking a complement in that of a characteristic vector. Yes, whereas D2n has dual L star equals Z2 plus Z2. Yeah, so they're quite different, and I, you know, at the moment I don't know how to do this one. I'm sure it's not very difficult, but so you know, I started telling you. I mean, I have this serial sheet that said I know how to start doing D7. Right, this is its Cartel matrix or something. I'm sorry. Okay, so I finished everything I've got to say.